Welcome back, guys. So today we're going to be discussing some proof techniques, like the basic proof techniques, kind of like the foundations of where you can build off of using the content that we learn in the future. In the past couple episodes, we discussed some notation and some logic behind proofs, like truth tables and how to write proofs. And then we also talked about implications. Today, we're going to be discussing proof techniques, so some basic ways of proving. Well, if you recall, mathematical statements, they have truth values, right? As we discussed in the past, which means true or false, right? And sometimes it's given to us. It's pretty obvious whether it's true or false. So it's like, oh yeah, this statement is true or this statement is false. But oftentimes, it is not obvious. Sometimes, not obvious whether true or false. So sometimes we can't simply just be like, this statement is true or this statement is false, right? And how can we show this? Well, we can prove, which means proving it true, or disprove, which means false. So if we prove something to be true, if we prove something, we're showing that it's true, and if we disprove something, we're showing that it is false. So now we can show how to prove universally quantified statements, right? Which we discussed in the previous episodes, right? So we have something that looks like this, right? For all x, right? Well, how can we prove this? Well, we know this means for all, which means one value of x in the domain that does not work means it is false, right? That's how you would disprove it. But to prove it, that means all values of x in domain hold, right? Well, so that means that we need to show that it's true for all x. Well, how do we do it with something like this that looks like for all x that's a real number, x squared plus 1 is greater than or equal to 2x. Well, let's consider x minus 1 squared. Let's consider this. We know that this is always greater than or equal to 0, right? We know that. Because if we were to graph the graph of this, it would look something like right? And this is definitely greater than or equal to 0. So now if we try to expand this, we get x squared minus x plus 1 is greater than 0. So that means that we get x squared minus 2x plus 1 is greater than 0. Now if we add 2x to each side, or we bring this onto this side, we get x squared plus 1 is greater than or equal to 2x. And we end up proving this is true for all real x. And that's all we have to do. That's all we have to show. That this holds because we know this, right? Now, what if we have to disprove it? I kind of talked about this earlier, briefly mentioned it. But what if we have to disprove it? Quantified, right? Well, if we have to disprove it, I discussed that right here. One value of x in the domain, when it doesn't work, means that the entire thing is false. So essentially, if we have something that looks like this, we need to find an x in the domain such that p of x is false. And this process right here is called a counter example. And this will be very useful when disproving universally quantified statements. So again, let's consider an example. Let's consider where we have p of x is equal to x squared greater than 0. And let's say our domain is for all real x's, we have x squared is greater than 0, right? So if we have for all real x's that x squared is greater than 0, then we need to consider some value of x. 1x, where this is not true, where it's false, right? Well, x squared at x equals 0 is equal to 0. And 0 is not greater than 0. It is 0 is equal to 0, which means at x equals 0, x squared is equal to 0 and not just greater than 0. Well, in this case, then, this is false at x equals 0. Why? Because if this was x squared is greater than or equal to 0, then yes, it would hold true. But because it's not that, and there's no is equal to, that's why we end up with a counter example. This x equals 0 is a counter example to this statement. This is a counterexample to this statement because we found an example where it's not true, and we know that for all real x, it's supposed to be true. All right. So when we're trying to disprove universally quantified statements, we would use counterexamples. Okay. Hopefully that makes sense. And now we'll move to proving existentially quantified statements. So now if we're trying to prove an existentially quantified statement, using the knowledge that we have from previous weeks, we know that this would be x, there exists an x in some domain such that p of x would be true. So how would we prove this exactly? Well, to show this is true, we can just solve an equation. We can just solve for x in p of x. Now, let me show an example. So I have the example where I have there exists an x that's an integer such that, let's say, x minus 2 is equal to 3, right? Well, I can just solve x minus 2 is equal to 3, where I get x is equal to 2 plus 3, which means x is equal to 5. And 5 is indeed an integer. 5 is an integer, which means it is true, because there exists an integer, which is 5, right? There exists an integer, which is x is equal to 5, where this holds true. 5, right? So it's easy to prove an existentially quantified statement because if there exists one value, if there is one value, then it's true. So as long as there is even one value, a minimum of one value, min one value, in domain. So as long as there's at least one value in the domain that proves it to be true, this statement will be true. Now what about disproving it? Right? Well, what if we were to disprove an existentially quantified statement? Well, in this case, we'd have something, again, that looks like this, right? We'd have this. It's much, much, much easier to, let's say, find the negation of this, right? So negate this, right? So then you get for all x in the domain, we have negation of p of x. And now we can try to prove this to be true. Why? Why would we prove this to be true? Because when negation is true, our original is false. And when negation is false, original is true, right? So when our negation is true, our original is false. When our negation is false, then our original is true. So if we prove this to be true, then we're proving this to be false. It's as simple as that. So now let's take a look at an example. Let's take a look at an example where we have there exists x, which is an integer, such that 3 over x is equal to 5. Well, negation of this would just give us x for all x that are integers. 3 over x is 5. Is this ever true? Well, not necessarily, right? Not necessarily, because if we solve for x here, we get 3 divided by 5, which is equal to 0.6, which is not an integer, right? Which means for all, the negation of this would be where it's not equal to, right? So we get 0.6, which means the only solution to this where x is not an integer. So if x is not an integer, that means that we've proved this to be true, because we've shown that for all integer values, it's impossible for 3 to be divided by an integer and get 5, right? And the only solution to this is 0.6, which is not an integer. In fact, x would be a rational, but not an integer. So we've shown this to be true, right? We've proven that to be true, which means that this must be false, because we've proven the negation to be true. And there we go. That's our proof for that. Now, we can move on to proving implications. So again, if you remember, A implies B, right? This is our notation. And let's say we remembered that this was our hypothesis and this was our conclusion, right? So if A is our hypothesis, B is our conclusion. Now, think of a science experiment. You would make a hypothesis and you would try to prove that the conclusion aligns with your hypothesis, right? So we can assume A is true to prove B, right? Because you use A and try to prove it. So this can be a starting point right here. So start here, and then you have to end here. So you use A to try and prove that B is true, right? So Now let's consider an example. So we say that for all x is an element of integers, if we have that x plus 1 is greater than x, then this implies that x minus 1 is less than x, right? How would we necessarily prove this? Well, if we start here, right, so we assume this is true, right? Well, then that means that subtracting 1 from each side would also be true, right? So then we get subtracting 1 from each side, so x plus 1 minus 1 gives us x minus 1, must also be true, right? And if this is true, then that means that x is greater than x minus 1 is true. And that's essentially what we have here. So we've assumed this to be true and proven that this is true. Make sense? Okay. Now we're going to look at proof by contrapositive. And proof by contrapositive says that if we have A implies B, right, then we can write this as negation of B implies negation of A. And what does this exactly mean? Well, now we just have an implication. So we can assume negation B to be true to prove negation A. And from before, if contrapositive is true, original is true. And if it is false, original is false. Okay? So it's directly proportional. So if contrapositive is true, original is true. If contrapositive is false, original is false. And this would look something like this. Well, how would we exactly prove this then, right? If we have something that looks like this, how would we exactly prove it? Well, let's use an example. So for all x that is an integer, right? If 2, so let's say if 2 times x plus 1 is, let's say, is equal to like let's say 3, then we get x is odd. Okay. Well, what would the contrapositive of this be? This would be x is even, right? I should make this that there exists some x. That'll just make the proof make more sense, right? So there exists an x where 2x plus 1 is equal to 3, and that implies that x is odd. Well, the contrapositive would be x is even implies 2x plus 1 is not equal to 3. So let's take a look at this example. If this is our original statement, then we have that this is our contrapositive, right? Well, okay, so now let's assume x is even, right? Let's assume x is even and show this. So assume x is even, right? And then we have 2x plus 1 is not equal to 3, which means 2x is not equal to 2, which means x is not equal to 1. Well, 1 isn't even, right? It's odd. And we know that if x is even, then it implies this, but we know that x cannot equal 1. So which means x can be any number except 1, but 1 is odd. So it does not contradict our assumption of x is even, which means that we've proved contrapositive true, then which means original is also true, right? So if we've proved our contrapositive to be true, we know that our original is true. Now, what is this type of proof called that we just did right here? We made an assumption that x is even, and we got that x is odd, and so it's not a contradiction, right? Well, what if it was a contradiction? What is a contradiction? That's exactly what our next proof method is going to be. Proof by contradiction. Okay, so now, what is a contradiction? Well, if I have a statement A saying A and negation of A is true, is an example of a contradiction. Why? Because let's say we're saying true and false. So we're saying true is true and false is true. But this is a contradiction because false cannot be true and true cannot be false. So they contradict each other. They cancel each other out. Interesting, right? So how would we exactly go about this? Well, you can assume the negation to be true. Right? So assume that the negation of the statement is true, and then try to reach a false conclusion. So try to reach something that will end up, like negating out or like kind of contradicting your like basic mathematics or your statement. So this can be a little bit confusing, but hopefully we can figure it out. So let's say that we have a statement that says, prove there is no greatest integer. Right? So prove by contradiction. So we're trying to prove that there's no greatest integer. So what we can do is we can assume the negation, which is there exists like let's say x that is a natural number, right? Such that n is less than or equal to n, x less than or equal to x, sorry, and for all n that are natural numbers. Okay, well suppose n is equal to x plus 1, right? So suppose n is equal to x plus 1. Then we get x plus 1 is less than or equal to x. Well, this is a contrapositive, right? Because a number plus itself, plus 1, cannot be less than or equal to itself. It always has to be greater when you add 1, right? So this contradicts this. Okay, well, what does this mean? This shows there is no largest integer. positive integer. Because, oh, sorry, I forgot to write positive integer here. That's why we're using natural numbers, because again, natural numbers are positive integers. Okay, what if we have to prove uniqueness? You might be thinking, what do you mean? What do you mean proving uniqueness? Like, what does it mean for something to be unique? Uniqueness is where solution is the only solution, right? So always this is a two-step process. I'm going to show you my two steps and then an alternate way of doing it. So prove there exists a solution. So first try to find a solution. First try to show that there exists at least one element x in the domain that satisfies p of x, right? Such that p of x is true. Next, what I like to do is you can assume let's say that so p of x is true and some other value. So like let's call this like p of like a is true, and denote and like deduct that x equals a. So you're basically showing that that's the only solution possible. So assuming these two, you get that this is the only one possible, right? These are the ways I would do it. Now here's an alternate way, right? So again, you find uniqueness, you find there exists, so find at least one solution. X in the domain such that p of x is true. Same step one. Now for step two, there's a way you can do it a little bit differently, right? You can assume p of x and p of a are true, right? And that x is not equal to a. So you make this assumption, and then prove that this is a contradiction. Again, using what we had earlier, proof by contradiction. So let's consider an example. So if we have an example where we have x plus 1 squared is equal to 0, we need to show uniqueness. Well, our solution we found is x is equal to negative 1, right? So now we assume x is equal to negative 1 and x is equal to some a, right? That's true, right? Well, now if we were to show x minus 1 equal to 0, we get x is equal to 1 and x is equal to 1. So we can denote that this forces a to be equal to 1. This has to be true because that's the only factor possible, right? So this forces a to be equal to 1, which means that this solution is unique. Right? That's how you would prove that something is unique. Now, if and only if. So the last thing I want to discuss in today's class, and then we will move on from there. So, an if and only if statement has a form that looks like this, right? And we also discussed that this is equivalent to saying right? So what you do is there are two steps. Again, so you would show that. So there's two steps, and the two steps would be, well, you prove is true, then you prove B implies A is true. If both are true, then A double negation B is true. If either is false, then false. So one of them must be true. Okay, let's go back to saying this statement, right? Where A equals rains. This is the example I used in the last video, and this is rainbow, right? So I can split this up into this format, right? So I can say I have to prove if it rains, does it imply that there's a rainbow? Well, what is a rainbow? Light goes through a certain medium, in this case, water, right? So yeah, we can say that every time it rains, there will be a rainbow. Now, is it the same backwards? Does a rainbow always imply rain? And I would like to say no. Why? Because if you point hose to sky, you will see a rainbow. Does that mean that it rained? No, it does not mean that it rained. It meant that there was presence of water and the presence of light, but that does not imply rain. So we know that this is indeed false in that situation. So we got, yeah, if it rains, there will be a rainbow because there's a presence of water and light, and rain provides water, but rain is not the only source of water, which means that that's false, which means that this is overall false. All right, I hope this made sense, and this was all I had to cover in this video. In the next video, I will be going over some divisibility and potentially induction. If not, we will go over that in the future videos.